Everybody has seen the announcement. Yes, I'm moving the test day. Exam 2 is not going to be on Monday, February 23rd. It's not going to be on Monday a week from now. It's going to be on Wednesday, March 4th. Okay, so we will have a little more time to study. This does not affect the dates of the other exams. Okay, so exam 3, exam 4, and the cumulative final, that's this determined by the department. The other exams do not change at all. Okay, and so that was the important update. Now let's look through all the stuff that we didn't look before and things that we have to cover this lecture. Okay, so we had stopped talking last time about the venous return, right? And that is the amount of blood that gets back to the right atrium, right? So when the blood is returning through the vena cava, it goes back to the right atrium. And an interesting thing about that is that the volume that gets back to the right atrium, it really has to be the same volume that gets pumped out of the heart through the left ventricle. Okay, so this is what really keeps that whole system as a closed system, and really the whole idea of your systematic circulation. Okay, and also pulmonary circulation. It has to be the same volume of blood that's going in. It has to be the same volume of the blood that goes out. So when the blood is coming back to the heart, it is going to follow, as we have seen before, it is going to follow the flow that is dependent on gradient in pressure. So the blood is always going to go from the area of more pressure to the area of less pressure. Okay, that's the main driving thing for the flow of blood. Okay, so how is it that the blood is going to get back to the heart, right? We have like the whole body system of veins that a lot of the veins are really below the heart, and the blood really has to go against the gravitational pull. It has to go against, right? The gravity is pulling down. It has to go against the gravity, and we know that at the time the blood gets to the tissues, really the blood pressure goes down a lot, right? So you remember that at first you have a very high pump to that blood pressure at the larger arteries. Then as you go down the lower arteries, the blood pressure goes down. By the time you get to the venules and the vein, the blood pressure is minimal. It is about 15 millimeters of mercury or so. So it's not really a lot of blood pressure that is going to be pushing this thing around. What is really important is that change in the gradient of that pressure. So by the time the blood gets back to the right atrium, the blood pressure there is nearly zero. It's not totally zero. We have flow going, right? But it's nearly zero, right? And then again, how is it that the blood is going to get more momentum and pressure? What is it going to increase the pressure after the blood gets to the heart? This is when I check if everybody's awake. Okay, what is going to increase the blood pressure? Anybody want to attempt in the back? Yeah? You are thinking too much. But you get a chocolate just for thinking about that. I actually asked a very, very simple question. Oh, good catch. Oh, that was perfect. All right. So, your blood gets back to the vena cava, gets to the right atrium, really close to zero pressure. Is it going to stop there, sit there, never move again? No. If it does, what's going to happen? You die. So what is going to get the pressure up again? I'm going to have a heart attack. I love the heart puns. Yes, the contraction. Yes. That's why your blood, oh, good catch. That's why your heart has to pump. It was actually a simple question. I do hope that everybody's just feeling the Monday back to school type of brain lack of action, right? Let's wake up. Okay, blood is going to move again just because your heart pumps. Because if it doesn't pump, then it's going to stop. Then you're going to have zero pressure, non-compatible with life. Okay, so what's going to happen now? When your blood is in the veins, remember a lot of the blood, like 60% of it is in the veins, right? When your blood is in the veins, it is going to be going back to the heart, right? But remember the pressure is low, so you have to have some certain strategies to help this blood to make it back to the heart, okay? Of course, the main driving force is the change in pressure, but also you have to help that blood to get back there. So what is it helping the blood to get back to the heart? First thing is the presence of those valves at the veins, right? So the valve is going to go help one unidirectional flow, unidirectional going this way, right? Is going to oppose backflow of the blood, okay? And three other things are important for pushing the blood back to the heart. One thing is this thing called the skeletal pump. The other thing is the respiratory pump. And then you also have this sympathetic tone, the sympathetic constriction, vasoconstriction. Okay, so let's look at these terms. First thing about the muscular pump. That means, especially with your leg muscles, right? It means when you contract the muscles, you are going to squeeze the veins, and when you squeeze something that is in a tube, the fluid is going to go away from the squeezed area. The fluid could go this way or it could go that way, but it's not going to go that way because you have a valve that is blocking the flow going that way. So when you squeeze this tube, the blood can only go this way if you have competent valves, right? So you squeeze the tube, you push the blood that way. That is called milking of the blood vessel, okay? So here is the motion. You squeeze the tube, you push the blood up. When you relax the muscle, then of course your valves are going to close here, right? So your blood is not going to go the other way. And also notice that when you squeeze the muscle, the valve that is going away, like down the opposite way from the flow that you want it to go, that valve is closed. You see here, right here, the valve is closed. Okay, so when you squeeze the tube, the blood will only go in one direction. All right, so that's your muscular pump. That's easy to follow, right? Quite intuitive. Okay. All right, so here's another picture here showing your muscular pump and your blood flow. Okay, and then you have these other terms here. This one here, the respiratory pump. Now, you really have to think on what this means and what it's doing, okay? Every time that you breathe, something is happening to your thoracic cage and something is happening to the muscles, right? So let's think about the diaphragm. That's the most important respiratory muscle. When is it that the diaphragm is contracting? When you breathe in. So that means you're contracting the diaphragm and you're pushing that muscle down. What is happening to stuff that is under your diaphragm? Okay, let's take a deep breath. What happened to your belly? It goes out. Stuff under the diaphragm gets squished, right? Yes, everybody felt that? Yeah. What happens to the veins that are in that region? They get squished. So that's the same principle of muscle milking, right? It's a muscle pump. You squish everything under the diaphragm and whatever is in the veins is going to be pushed to one direction, the only direction that it can go to, which is back to your heart. Okay. Now, when you are inhaling, what is happening to your thoracic cage? is expanding. That is causing a negative pressure in all this cage, this stuff that is caged, right? This is how your lungs are going to expand because you cause negative pressure. Now, everything else that is up there, up from your diaphragm, is also going to feel that negative pressure. So the blood that is in your veins in that session, they are going to feel that pressure, and it's like a straw that is getting sucked with the negative pressure. Okay, so that helps to pull the blood up. So you're at the same time that you're squishing the under the diaphragm area, the abdominal area, at the same time that that's being squished, you are pulling the blood by a negative pressure of your thoracic cage. Okay, so this is what you call your respiratory pump. Is it always working? All right, let's go for a vote. How many people think yes? Okay, got a vote. Okay, go for it. How many people think no? Okay, how many people are just not thinking or don't even know what the question is? Oh, I honest. I like that. You get a chocolate. Let's increase your sugar in the brain. Okay. Now, question is your respiratory pump always at work? Let's give it a test. Try to make it stop. Hold your breath. How long can you hold your breath? Depends on your will. There were some little kids that could hold their breaths when they didn't get their way, and they would actually hold their breath until they would pass out. Guilty. It was me, yes. And you can imagine my mother thought I had some very serious neurological problem, and they rushed me to the emergency room, and the doctor would say nothing is wrong with her, but she fainted again. And then one pediatrician told her, well, next time she faints, leave her on the floor. And then I realized that fainting was not going to get my way. But yes, you can try to stop your respiratory pump, but not for too long. Because if you try to stop it for too long, you're going to faint, and then autonomic nervous system is going to pick up, and some centers in your brain, like at the medulla oblongata, they're going to trigger you to start breathing again. Because if you don't breathe for a very long time, what's going to happen? You die, right? So this thing is really always at work. Okay, respiratory pump, you can briefly interrupt it, but it will go back to work. Okay, so this is all helping your flow to keep on flowing. Okay, so besides those pumps, you also have sympathetic vascular tone. Okay, it's also called vasoconstriction. So this is a continuous, yes. Well, what do you think?
You said it does stop for a little bit, but then it turns back on. But then you also said that it's still always at work. But if it stops for a little bit,
Yeah, you can interrupt it briefly, but it will go back to work and is always working. Yeah. You cannot interrupt it for too long because that is not compatible with life. So the question is it always working or is it not always working? Well, it is always working. Okay, it's always working. Even when you try to stop it, you're going to be very uncomfortable. You're going to be thinking about restarting it like very often. Okay, so yeah, it's always at work. Okay. All right, so we have here your sympathetic vasoconstriction that is always sending a little bit of norepinephrine through your nerves and is always keeping those blood vessels in this vascular tone. Okay. All right. So here, that idea of your blood pressure, right? Remember, at first you have your pulsating pressure at the large elastic arteries. Then you have here distributing arteries, muscular arteries. And then you have your drop, the big drop the big drop in the blood pressure that is happening where? When you start getting, you're getting your laminar flow, where you're going to see that, which is not showing here, actually a little bit. It's going to be at your arterioles, right? And then you're going to have your capillaries. There's going to be laminar flow relatively low, and then the veins, and back to the vena cava that goes, you know, to zero just before, I mean, very close to zero until it enters the heart. Okay. And here comes your first question. I do have a lot of questions for you today. Hopefully you'll be able to get through all of them. Okay. What effect does prolonged standing in one position, that means without walking around, right? What effect does it have on blood flow? So you got to think a little bit about this. So the first answer is that it causes blood to pool, blood pooling and slowing of the blood flow. Then the other possible answer, it causes a compensatory decrease in arterial pressure. Yeah, that one you have to think like in negative term. Okay. Then here it says it causes a sharp decrease in heart rate. It's like, it causes a sharp decrease in respiratory rate. That's also weird. Okay, so you really have two answers that could be plausible. So your answer here is A. Actually, the original question I had taken from Pearson, and they had a mistake that was in the previous version of your PowerPoint. The original answer choices here, it said it causes a compensatory increase in arterial pressure. And that is also true, but we're not getting there. That's too complicated. Okay, so the correct answer here is it causes pooling of the blood in the legs and slow down a little bit of that blood flow. All right, so here, the idea of how fast the blood is flowing now, okay? Now, this idea is not very intuitive sometimes, okay? So we have to really make sure that you understand what is happening here. So basically, the velocity or how fast the blood is flowing is saying here is inversely proportional to the total cross-sectional area. This is red and is bold and is underlined. Okay, total cross-sectional area. What does that mean? Well, at first, when you look at a diagram like this, you see that the big vessel is like a garden hose, right? And then it becomes smaller. And the first thing that comes to my mind, or that came to my mind when I was looking at this at first, was that if I am outside watering the grass with my garden hose, and I need to water the grass at the corner, and I'm too lazy to walk over there, what am I going to do? Spray how? Okay, let's put into words what you're thinking. You squish the garden hose, right? You squish it, you make the diameter smaller, and now you're going to have a stronger flow to reach all the way in the corner, right? Which is true, right? That is what happens with the garden hose. But your circulation, your arteries are not really working quite like a garden hose, because you are not only diminishing the diameter, you're also branching out the diameter. You're branching out the blood vessel in general. So here, if you're just squishing the aorta, then yeah, you're going to have more blood flow. You have more velocity of the blood flow. It's going to reach more places, right? But here, you are dividing it into a lot more arteries. You're going from your elastic arteries into, let's say, your distributing arteries. And now, if you look at the cross-sectional area of your aorta in comparison to the sum of cross-sectional areas of the branching arteries, those cross-sectional areas are larger than your cross-sectional area of the aorta. So now you are really going to distribute that flow into more areas, that means your flow is going to slow down. And then when these guys branch further, you're going to have more areas of cross-sectional areas here in comparison to these guys over here. So you look here in the graph, and it's telling you the total cross-sectional area of your blood vessels. So we start here with a very relatively small cross-sectional area when you're just looking at your aorta. And as you start branching out those arteries, your cross-sectional area increases dramatically. When it gets here to the arterioles, look what happens to your cross-sectional area. It jumps up a lot. It's a lot of area of these blood vessels. Okay, so obviously at your cross-sectional area here with your arterioles, your blood pressure is going to plummet over there. Okay, so your blood pressure starts high, and then it goes down, and then way down until it gets to the capillaries. And that's what you need to have at the capillaries, because remember, your capillaries are very, very delicate, one layer of cells, and you need to do all the exchanges down here, right? So you don't want very fast blood flow, or you're not going to have time to deliver your goodies, and you're not going to have time to pick up the waste, right? If you're going very fast. Also, if you're going very fast here, you might damage the blood vessels. You don't want very fast flow. You don't want a lot of pressure there, okay? So remember this type of inverse relationship with the velocity of the blood flow and your total cross-sectional area, okay? So just for analogy, then I put this picture here, right, showing your pulsating blood flow in comparison to your laminar blood flow, and here is showing the velocity. Okay, fast, 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 slow, and then picks up velocity a bit more when it goes back to the veins, because here in the veins, you're going to have merging of those smaller veins into your larger veins, and when it gets up here, close to the aorta, your velocity picks up a little bit. But your pressure is a lot lower, is the lowest that you can get, right, over there. So the analogy here is with the distribution of highways and local streets in a city, right, in a map. So here we have our, let's say that this is the I-95, right? So in a major highway, you can go relatively fast, right? But if you have the mission of delivering groceries to a certain house that is all the way down here in the periphery, so what you're going to do? You're going to come out of the highway through the exit, and you're going to slow down, and then you're going to go to local streets, and hopefully you're going to go slower and slower until you get to your destination house. And then you're going to nearly, well, practically speaking, you have to stop and deliver something, and then pick up the waste and keep on going, right? Although in the arteries, you're not, in the capillaries, you're not totally stopping, right? But you're slow enough to pick up and deliver stuff, right? What happens if you go very fast here? Well, you're going to crash into somebody's house. Not very good, right? So it's just this analogy that you have to match the function with the everything else that is going in there. Okay, so it's lower velocity, deliver stuff, pick up stuff, and then you get back to the circulation with a bit of a higher velocity. You go back to 95, right? Okay, so everybody's cool, everybody's clear with those concepts? All right, so here, getting a bit fancier, okay? So now we're going to talk a bit more about the flow, how fast it goes, right? And resistance of blood vessels, keeping in mind that the main push for your circulation is the change in the pressure gradient, right? So this here is telling you that the pressure gradient from where it started to where you're going to where you're finishing, right, is equal to the blood flow times the resistance. So change in the pressure is blood flow times resistance. do a bit algebraic manipulation of the equation, and you say that the blood flow is equal to the change in pressure over the resistance. Okay? So what does that mean? It means that if your resistance goes up, your flow goes down. Everybody got that? Intuitively speaking, if you squish the blood vessel, that means your resistance go up, your blood flow is going to slow down. Okay, resistance is the opposition, opposing the flow, right? Now, let's say that you start up, right? You're starting up the flow of the blood and with the highest pressure with your heart, right? Your heart is pumping. So when your heart pumps blood to all of your tissues, to all of the organs, you really have to take into consideration that increasing your cardiac output is really going to increase the flow to all of those tissues at once. Okay, so the change in the pressure, how deep you go into the delta P, that is really going to dictate how much blood it gets to your tissues. Okay, so let's see here the relationship of this blood pressure with the flow and the resistance. Okay, so here we're saying that if you have a huge change in pressure here, if you have a huge change in pressure, then you're going to increase your blood flow. Okay, so flow is going to be proportional to the change in pressure. The biggest the change in pressure, the biggest the blood flow. If you put resistance in your blood vessels, you're going to have less blood flow. Okay, that's pretty simple. Okay. Now, what is going on here? I like this statement saying that the body doesn't really care about the math, right? So don't get too worried about that. What you have to worry about is really your intuition on what is happening. Okay. What is happening here is that the body really needs to regulate that flow to the organs depending on what the organs need. Okay? So main idea is that the flow is going to be proportional to the changing pressure and inversely proportional to the resistance, as we have seen before. Okay. So here is when we start thinking about if you increase the cardiac output, right? So let's say here that your heart starts to pump harder and pump more volume of blood because of the cardiac reserve. When you increase your cardiac output, then you are really going to increase this initial pressure and the pressure gradient, and you're going to increase that to all of the organs that are receiving the blood. So that drop in the pressure is going to be really bigger for all of the receiving tissues throughout the blood. Okay. So keep in mind that when you are increasing that flow, you are also going to be putting more pressure on those organs. Depending on the organs, they cannot deal with a lot more pressure. There are some organs that are very sensitive to any change in blood pressure. So they really have to regulate how much blood gets there. Okay? And there are certain organs that really have to keep a very constant flow, constant pressure. Otherwise, they're going to malfunction, right? So what's going to happen here? Remember that you can control the pressure and the flow basically by controlling the diameter or the radius of your blood vessels. And remember that this change in the blood vessel is very, very important at the arterial level, right? So the organs are going to tell the arterioles how much to dilate or how much to constrict based on your cardiac output, based on your blood flow, okay? And just to refresh your mind, what is this relationship of flow and diameter? So here, getting from the beginning, the first equation we looked at, it says that the resistance is inversely proportional to radius at the fourth power, right? Remember the equation, everybody? Yeah? So if you change the radius, you're going to change the resistance, right? So let's see what happens here. The flow is proportional to the change in pressure over the resistance. You can play with the math and practice this on your own, right? Basically, what this is telling you is that if you change your radius by a factor of 4, either shrinking it or dilating it, you are going to change the flow by 256 times. So just by changing the radius, you can control the flow like a lot. If you change the radius by a factor of 4, your flow will change by 256 times. Okay, do the math just to make sure you convince yourself of what's happening. Okay, so basically your arterioles are the vessels, are the blood vessels that are going to control how much blood gets to the tissue, depending on what the tissue needs, because everything has to work in homeostasis, right? So now we're going to start seeing how is it that the organs control that flow, okay? And this is the part that I get people that start having a headache. But it's not that complicated, really. Some things that you really have to focus on here. Okay. So you can have 3 forms of control, mainly 2, because 2 of them get put in the same bucket, okay? So 3 forms of control here. The first one is happening at the level of the tissue itself. The first thing that happens is this auto-regulation. So this is intrinsic control because it's happening at the tissue, very local control, okay? The other type of control is extrinsic, and then you have 2 types of extrinsic control. So those are coming out, they're coming to the organ, but they're coming from somewhere else, okay? The first one is a control of your central nervous system, so that's going to happen through nerves. Okay, so brain here, and we're going to send a message. That's a very fast type of control, okay? And of course, it's coming it's coming from outside of the organ, so it's extrinsic. And the other extrinsic level of control is at the level of hormones, because you're going to have some cells like somewhere else that are going to produce certain hormone that is going to get into the blood circulation and then reach your organ and control the flow of the organ. Okay, so you can imagine this type of control is slow, right? So when you think about CNS control, you think very fast. When you think about autoregulation, is also relatively fast, but when you think of hormonal control, that's slow. Okay. So now let's see what happens here. So first thing you think in mind is what is happening in the tissues. Okay, so we know that you have to deliver oxygen and nutrients, and you have to pick up the waste, right? Now, when you look at tissues like in your lungs, you have to do the exchange of gases, right? You also do exchange of gases in the tissues, right? You deliver oxygen, pick up carbon dioxide. Opposite happens in the lungs, okay? Now, when you look at your gut, you also have to pick up nutrients, right? And also, when you think about absorbing nutrients in the gut, that doesn't really go straight to the bloodstream. You actually have to pick up those nutrients with some other system. Actually goes like lymphatic system, pick up those big molecules. And then that takes it to the liver, breaks it down, then puts in the bloodstream, okay? But you have all these exchanges of stuff happening, okay? And then you also have to control how much fluid is in your body, right? You have to control your blood volume by controlling how much your kidneys are going to expel, okay? Is going to excrete, okay? So urine output is also very important for control of blood volume, total blood volume, okay? So each tissue or each organ is going to receive exactly what it needs by controlling that flow of blood, Okay. So how is it that your body is going to control that? Well, basically, you are going to have these backup systems that if something gets out of the norm, out of homeostasis, you're going to have these negative feedback systems that are going to push the seesaw back to equilibrium. Okay? So what is it that you can control here? Basically, you can control the heart rate, so how fast your heart is pumping, right? That has to do with cardiac output, right? If you start beating your heart faster, you're going to have more cardiac output. Right? Then you can also control the stroke volume. So several items here that you should know, right? You have your cardiac rate. You have a stroke volume. You have here your arterial pressure. This is your blood pressure, right? And you also have your total blood volume, right? So all of this is going to control your overall blood pressure and flow. So your body has to adjust all of this in order to keep homeostasis. Okay, so here's another question for you. Okay. What is the primary factor that drives blood flow in the systemic circulatory system? Okay, let's answer quickly. Does anyone need more time? Yes? That is your most important factor that is going to drive your blood flow, is the blood pressure gradient. Okay. So now we're going to see all about these intrinsic controls and the extrinsic controls. Okay. So here, looking at the intrinsic controls, you know there's going to happen inside of the tissue, right? And basically, you're going to have certain cells that are very close to each other and they're going to work locally. So local control is what you call intrinsic control. Another name for it is autoregulation. Okay. And when you compare it to extrinsic controls, those are coming from outside of that tissue or organ. Okay. So here, the idea of your extrinsic control, that is really going to dictate what is happening to your entire body, okay? And one very, very important aspect of your extrinsic control is control of the diameter of your arterioles, as we have seen before, right? So now we're going to look at also what is happening inside the tissue when you look at those local arterioles. Arterioles are also important for control of blood flow inside the tissues, right? But this is going to be really after the organ feels a change in the blood pressure, in the flow, and then the organ automatically does some adjusting to compensate for that change, okay? So the organ controls like its own arterioles in order to regulate for the flow homeostasis. Okay. So let's see what is happening here at regulation of your intrinsic control. So local control. What is it the organ is going to feel and how is it that it's going to adjust? So the organ is going to feel a couple of things. They're most important here. It is going to feel if it has enough oxygen, and it is going to feel the levels of byproducts. Basically, it's going to feel the levels of ions and some other byproducts like adenosine, okay, and prostaglandins, but I like to focus on adenosine. It is a byproduct of metabolism, okay? Then what is going to happen here? When it feels some change, the organ is going to cause either relaxation of the arterioles, right? You're going to relax the like those little capillary sphincters. They're present in the arterioles, okay? And when it relaxes, it is mainly going to use the production of this very strong vasodilator that is called nitric oxide. So the blood vessels themselves are going to produce nitric oxide. So the cells of the blood vessels are those endothelial cells. Okay. So if they feel that not enough oxygen is there, the endothelial cells are going to produce nitric oxide, and that's going to dilate the local blood vessels to allow more blood to get in there, to get more oxygen to be delivered. Okay, so this is the process of relaxation. On the other hand, you also have some other products, some other molecule that is produced by endothelial cells, and that is endothelins. So endothelial cells, when they have too much oxygen, too much flow there, they are going to stop really the production of nitric oxide and start to produce endothelin in order to constrict those blood vessels. So these arterioles are always really at a balance. Do I have low oxygen? Okay, I produce nitric oxide. Do I have plenty of oxygen? Oh, yeah, so let's just keep the vessel a bit constricted, right? So it produces the endothelins. So it's a push and pull type of mechanism. Now, if you have both of them present, if you have both endothelins and nitric oxide being produced at the same time, usually the negative signal wins. So here, the positive signal means contract, the negative signal means dilate or just relax. So in this case, nitric oxide would win this push and pull situation. Okay? Everybody got that clear? All right. Okay, so let's see here how that thing is working as a whole. Okay, remember that when you are controlling flow in general, you have these two forms of control, right? Intrinsic and extrinsic, and you also have controls that are very, very fast and controls that are slow. Okay, so when you think about fast adjustment, you're really thinking about nerves. You're thinking about central nervous system control of that adjustment. Very, very quick adjustment. Okay, so it's controlled by nerves in the first place, and you also have local control, but local is always a bit slower than neuronal control. Okay. Okay. Examples of this type of quick adjustment is really what is happening, like when you have sudden change in let's say orthostatic position. So let's say that you are laying down in bed, you just woke up, but now let's say that you just, it wasn't just like a normal waking up situation. Instead of you just getting up slowly, you get up, it's like, oh, okay, let me hit my alarm clock, I would think about getting out of bed. No, let's say that some very loud noise happened and you jumped out of bed, and before you're even with your eyes open, you're already out of the bed. There was very, very quick form of position change, right, from laying down to standing up. Now, if you do not have very fast control of blood vessel, of blood flow, what would happen would be that your blood vessels are already dilated and pumping the blood to your brain. By the time you get up very quickly, your blood would drop from your brain, and you would pass out. Okay, so in order for that not to happen, you have sensors in your big arteries. They're going to feel the change in your position, and they're going to send very, very fast signals to contract those blood vessels and keep your flow steady so that you don't pass out. Okay, so that's a very fast type of adjustment that you see as a neuronal control. Okay. And then when you compare it to a slow type of controls, you're going to mainly look at hormonal control of blood volume and pressure. Okay, so then you're going to have some hormones that are being produced in one area, It can be at the suprarenal glands, it could be at the kidneys, or it could be at the hypothalamus, and then it has to go through the pituitary, be delivered in the blood. That's slow. That's going to take time, okay? So let's see here how that's happening. Important things that you have to know about this overall control. You have to know those factors that cause vasodilation, okay? And the factors that cause vasoconstriction. So when you look at intrinsic controls, or you're going to look mainly at metabolic controls, okay? So you're going to look at drop in oxygen, okay? So if your oxygen goes down, you want to open up your blood vessels in order to allow more blood to get in there and you get more oxygen delivered. And that makes sense, right? When you have increased carbon dioxide, that's the same story. You want to get rid of carbon dioxide, which means you want to bring more oxygen, so you want to dilate your blood vessels. These two levels here, let's say increasing the acidity, meaning increasing the hydrogen ions, right? Your hydrogen ions, it means that a lot of metabolism is happening and you need more blood there in order to keep up with your metabolism, okay? Again, I mentioned here your adenosine is a factor for allowing dilation. And of course, your nitric oxide is going to cause vasodilation. Okay, so those are all your intrinsic factors. Now, looking at extrinsic factors for control of your blood vessels, there are two main things about what is happening here that is not at the local level. Okay, one thing is if you are not stimulating your sympathetic nervous system, then your blood vessels will dilate. Okay. If you stimulate your sympathetic system, then they will contract. But no stimulation of sympathetic system means that your blood vessels will naturally be more dilated. Okay? And then there is this one hormone. Let me put here in red. This one hormone that is important for dilating your blood vessels. And this guy is called atrionatriuretic peptide. Okay? Where is it produced? Look at the name and you tell me where it is produced. In the atria, yes. Why is it produced over there? Let's think about it. So this thing is telling you it's a hormone produced in the atria that is going to dilate your blood vessels. So let's say now that you have a lot of venous return. It gets to your right atrium, right? It gets to your right atrium, and it's a whole volume. It's like this whole bolus of blood gets in there, and the atrium is like, oh my God, I'm gonna explode. That means I'm getting too much blood. The blood pressure must be high. I need to slow down. I need to lower this blood pressure or I'm going to explode. So then this atrium, some cells in the atrium, is going to produce this peptide, this hormone that is going to get in the blood. Okay, it's going to go into circulation. It's going to reach the blood vessels. It's going to reach the arterioles, and it's going to make them dilate. When the arterioles dilate, that is going to lower the blood pressure. So now the venous return, it's going to slow down too. Okay, so you're not going to have that poor atrium that's going, we're going to explode. Okay, no, I'm not exploding now. Okay, so that's the peptide, that's the hormone that your heart produces. Okay, and this is part of extrinsic control of the blood pressure. Okay, so that's the only hormone you have to think about for dilation of the blood vessel. Okay, now let's look here at your vasoconstrictors. Okay, you have internal control. One of them is the stretch of the blood vessel. If the blood vessel is stretching too much, because same idea as what the blood that came to the heart, if it's too much blood going to this blood vessel and is causing it to stretch too much, when the vessel feels the stretch, it will cause vasoconstriction on its own. Okay, so this is this intrinsic myogenic type of stretch. Myogenic because it has to do with the smooth muscles that are present in your arterioles. Okay. Another thing that is going to constrict the blood vessels is also the presence of some metabolites, okay, some metabolic components here, and we have mentioned here those endothelins, right? Remember, endothelin and nitric oxide are doing the balancing effect, okay? All right, so let's see here. Okay, so endothelins here, nitric oxide there, balancing, okay. So let's see here, vasoconstrictors that are extrinsic, okay? Here you're going to have your sympathetic nervous system. Increase your sympathetic nervous system, blood pressure is going to go up. You're going to constrict your blood vessels, right? And then you have all this hormonal stuff. That's the part that sometimes gives people headaches. But we're going to look at it in a very dissected way, and it's going to be easy, okay? So you're going to have here angiotensin, antidiuretic hormone, epinephrine and norepinephrine. These two guys put in one bucket because they do the same thing. Okay, the difference is that norepinephrine is produced by central nervous system. Epinephrine is produced by suprarenal glands. Okay, so these guys here are the hormonal control of your blood vessels, vasoconstriction. Okay. Okay. So here we go, starting with neuronal controls. So remember, you have the cardiovascular center at your medulla oblongata, right? Remember what the cardiovascular center is doing to the pacemaker of your heart? Cardiovascular center is very important also to control your blood vessels, dilation and constriction, okay? So let's see what is happening here. You have your medulla oblongata right there, and you have your cardiovascular center, and then you have here in the cardiovascular center, you have your vasomotor center, okay? Control of your blood vessel. You have a little area that is going to cause constriction, another area is going to cause relaxation. It's all in this area that is here at the cardiovascular center. Okay. When you look at the vasomotor nerves, you are going to see there are some sympathetic nerves, okay, and there are some parasympathetic nerves. Okay, so what is going to happen here? Your sympathetic nerves, they are going to cause constriction of the blood vessels. How is it going to work? If the sympathetic nerves are activated, they are going to use the neurotransmitter that is norepinephrine, and those are going to constrict blood vessels. Because in your peripheral blood vessels, you have receptors for norepinephrine. Those receptors at the peripheral blood vessels are actually the type of beta-1 adrenergic receptor. Norepinephrine is also called noradrenaline, okay? And that's the cousin of adrenaline. So epinephrine is adrenaline, norepinephrine is noradrenaline, and they all do the same thing, okay? So when they hit those receptors in systemic blood vessels, they cause vasoconstriction, okay? Why did I mention that? Well, because when it hits other types of blood vessels in your lungs, for example, it has opposite effect, but we get there later. Okay, so here, norepinephrine, epinephrine, they cause vasoconstriction. Okay, basically, you always have a bit of activation of the sympathetic nervous system because you always want to have a certain blood vessel tone. Okay, so vasomotor tone. Okay. So what can influence that cardiovascular center? Well, you have some impulses or some, connections with your higher brain. So here's your cortex, right? So not only your cortex is sending information, but also limbic system is going to send information to the cardiovascular center. Okay, and you can imagine that sometimes even by thinking about something, you can increase your heart rate and cardiac output and increase your blood pressure, right? Do you know people who are always worried about stuff and they end up with high blood pressure? Like your parents, for example, right? Not you guys, you're too young for that, right? But sometimes you see like some parents that they worry too much and like, you're giving me high blood pressure. Yeah, I tell my kids they're giving me gray hair, but yeah, anyway, I just want to make them feel guilty because it has nothing to do with hair. But anyway, so you have a certain areas in your brain that can send signals that are going to increase your blood pressure. Okay. Besides whatever you're thinking, you also have certain areas in the body, some receptors in the body. They are going to send signal from specific areas of the body. They are going to control vasoconstriction and vasodilation. And here are the ones that you should think about here, okay? You have proprioceptors. Those are going to monitor what is happening at your joints, right? So basically when you're running or when you get up very quickly, or basically when you're having movement, you have proprioceptors that are going to send information based on your movements, okay? And then you have these baroreceptors. That is the one that is going to monitor your blood pressure at specific areas that are very, very important for your whole body function, okay? You're going to see where in a minute. Okay. Then you're going to have chemoreceptors. And those are going to monitor stuff that is in the blood, like what is the level of oxygen, what is the level of carbon dioxide. Those are the chemical detectors, okay, chemoreceptors. They're going to monitor that, okay, oxygen, carbon dioxide, and also acid level of acidity of the blood, okay? Once the signals get to your cardiovascular center, then you can have a few outputs. You can either stimulate your sympathetic nervous system or not, right? If you stimulate the sympathetic nervous system, you are going to increase your heart rate and also do vasoconstriction. But then if you do not stimulate your sympathetic system, then your parasympathetic takes over and then you decrease your heart rate, okay? Okay. So let's see here what is happening with this sending of information and balancing of the homeostasis, right? So we're thinking about this negative feedback loop, right? And you're going to have to think about changing pressure and change of blood chemistry, and then how to adjust for those. All right. So let's look here at your baroreceptor. Remember, baroreceptor has to do with change in pressure. Like what pressure? What is the pressure that you're monitoring here? Okay, I didn't get used to this today. I see people in the back. Not you get people in the back, so you have a little time. What is the pressure that you are monitoring? Systolic pressure, yes, but you're thinking too much. Who said that? Okay, you got one. I don't even need that. Oh, didn't you get one already? Okay, you got one already. You gave it to her. Okay, here. Oh, okay. What is the pressure that you are monitoring? People from the back, I want to use this. Yes, who said that? Yes, all right, perfect. Nuts or no nuts? Nuts? No nuts. Okay, you're monitoring your blood pressure. This is when your sympathetic system takes over because everybody's blood pressure went, okay, especially the ones that are close to my aim. You see how your brain coordinates your blood pressure? All right, so keep sympathetic active. That was a disaster. Okay, you can only do this in big auditoriums, right? Okay, so this is blood pressure, yes. But where? Look at these strategic places. Look at this. You have blood pressure monitoring right at your aorta, right coming out of the heart. Okay, which one is the heart? I think it's this way here. Yeah, at the aortic arch, like right there, because this monitor, these little monitors cells, they are going to feel how much pressure is coming out of the heart, because it has to control what is the pressure that goes through the rest of the body. Okay, so placing these baroreceptors right there at the exit of the heart is going to send a signal that is going to control the vasodilation or vasoconstriction throughout the heart, okay, to keep it constant. Okay, and look at these guys over here. Those are right at the carotid arteries. You see, these are like internal carotid arteries. Where do these arteries go to? Where are they going? Huh? The brain. They are monitoring the pressure that is going to your brain. Very, very important. You want to keep a steady flow of pressure there, right? If you drop the pressure very suddenly and your brain doesn't get oxygen, doesn't get the blood, you know what happens, right? So those guys really, really have to keep on sensing the blood pressure, all right? So those are the two I just mentioned here. All right, so what is happening here? So let's say here that those receptors are going to cause this negative feedback that is actually a reflex, and because it has to do with the central nervous system, you call that autonomic reflex. It happens by itself, it's like automatic, okay? So let's see what happens here. If your blood pressure goes down, your receptor, that is your baroreceptor, is gonna feel it, is gonna send the information to your central nervous system, right? Remember, it's a cardiovascular center at the medulla oblongata, and that is going to send information back to constrict your blood vessels and get your blood pressure back to where it's supposed to be. Okay, everybody got that? Okay, it's a reflex that is going to keep the blood flow and pressure constant. All right, so here is straight from your book showing you what happens when you have a baroreceptor that feels changing stuff, changing homeostasis. So first thing that happens here, in this case, blood pressure goes up. Blood pressure goes up. So this guy here is feeling the blood pressure that is going through the blood, is feeling that it's getting squished physically. This is how he feels it. It's right at the wall of the artery, and he feels that it got squished. So when it got squished, it's like, I don't like it. Okay, this is the I don't like it part sends the information to the brain. Okay, then the brain, the medulla is going to send information back. It is going to go in two ways. First one is going to tell your heart to relax a little bit, right? Don't be so nervous, right? If your blood pressure is too high, you're going to tell your heart what is going to happen to your pacemaker cells. Remember what's happening in the pacemaker cells? They're going to start beating not very frequently. Slow down a bit, right? And then what's going to happen to your blood vessels? You are too tensed up. Relax, right? Because you want to bring homeostasis back. If the pressure is too much, you want to tell those systems to chill out, right? And then what's going to happen? After these effects, your homeostasis gets back into a regular state. Okay? All right. Oh, I guess a bit too fast. Okay. So here, what is going to happen here? Your heart rate is going to go down. Your total systolic volume goes down. Your cardiac output goes down. And you dilate your blood vessels. And then your mean arterial pressure also goes down, and you're back in homeostasis. Okay, here another question for you. Okay. Can you predict the baroreceptor reflex response to an increase in blood pressure? Oh, I just gave you the answer. Yeah. And so if you are awake, okay. So here having the opposite type of homeostatic imbalance, right? So you can just follow this on your own because it's actually the opposite type of negative feedback that we just mentioned here. In this case would be increasing sympathetic stimulation in case you have initial drop in your blood pressure. All right. So those are your baroreceptors. Now let's see what is happening here with your chemoreceptors. First, let's see where they are located. So they are actually very close to your baroreceptors, okay, also in the aortic body and in your carotid arteries, okay. So what are these guys gonna feel? They're gonna feel change in the chemistry of the blood. They're gonna feel mainly three things: carbon dioxide, oxygen, and acid. Okay, so that's gonna tell those receptors. It's gonna tell those monitor cells if you have proper oxygen or if you have too much carbon dioxide and too much acid. So what is gonna happen? If you do not have proper oxygen, then you are in a state of hypoxia. If you have too much acid, then you have blood acidosis. Okay. In both of these cases, you need to dilate your blood vessels because you need more blood to get there. And also, well, if you have too much carbon dioxide, because by the same idea, if you have acidosis, so hypercapnia is the term used for too much carbon dioxide. Okay, so in this case, you really want to do what? Dilate your blood vessels because you need more stuff going there. Okay, so here, what is happening here? I just mentioned this before. Okay, this is actually in a bit strange place here. Okay, so what is going to happen here? You are going to not only send signals to the medulla to control your blood vessels, but you're also going to send signals to the respiratory center that is going to control your breathing rate. Okay, because these receptors are monitoring also levels of oxygen and carbon dioxide. So if they feel that your levels of oxygen are low, then it's going to stimulate your lungs to start breathing faster so that you can oxygenate your blood at a faster rate. Okay? All right, so let me see if this is also important. Okay. Oh, look at this. Another question. Told you, tons of questions today. Baroreceptors detect change in what? Okay, you can just answer this question based on elimination. What is your answer? B. Your baroreceptors, they are going to feel pressure change. What pressure? Pressure that is in your blood vessels, right? Okay. All right, so I'm just going to start with this slide, but we're going to pick up on Wednesday because this is the part that gives you a headache, and I don't want to give you a headache right on Monday. Yay. Okay. So what is happening here? Hormone. No, don't go yet. This is important, huh? Don't go yet. Hormonal. We got the hormones. Okay. Hormones. They're going to control your blood pressure. You're going to have here renin, angiotensin, aldosterone system. That's the most important one in a hormonal control. You also call the Ra system. Okay, Ra, that's the guy. Okay. You're also going to have, of course, epinephrine and norepinephrine because those can also be hormones. They're not only neurotransmitters, but they're also considered as hormones. Okay. Antidiuretic hormone. The name is telling you what it's doing. What is it going to do? Okay, what does a diuretic do? Diuretic makes you pee. Antidiuretics makes you not pee, exactly. And then you have this guy here. Remember, natriuretic peptide? That's your only hormone that is going to dilate your blood vessels. All right, So we pick up this on Wednesday.